Well, hello. My name is Fernando Raffan. I'm a graduate student, master's student here at the University of Maryland, and I'm working for the Fire Protection Engineering Department and Aerospace Engineering Department under the guidance of Dr. Andre Marshall in fire protection, Dr. Chris Cadu in aerospace. What I'd like to talk to you about today is there's a phenomenon called film cooling. It's a process, a technique that is used to help us protect gas turbine engines in a plane like this one, for example, and also rockets. So basically what happens here is you mix fuel, you mix air, you get these hot combustion gases, and then that's what eventually what will produce the thrust in these engines. But it's so hot that really you have to protect every component in the engine from melting. So this technique called film cooling is aimed at doing precisely that. This technique has been around for a while, early work around in the 1950s. So we know it works, but we don't really know exactly why. So we want to understand exactly why it works and be able to get some experimental data out of this. So here's two schematics. We have gas turbine engine inside, so just like that one, but the inside. So we have combustion gases in this direction, and then there's cold air injected along the walls tangentially. So this acts as a shield that prevents the walls from actually seeing the full heat of these combustion gases. And something similar in a rocket, it's the same thing. You have fuel and oxidizer mixing, flow going in this direction, and then cooler gas right here. So we know it works for these two propulsion systems. So we want to basically simulate this in a laboratory environment. So what we have here is a hot wind tunnel that was developed specifically for this kind of research by Dr. Andre Marshall and a former grad student that just graduated, Carlos Cruz. What we have here is a fan basically driving the wind tunnel, so you can achieve speeds in the order of 25 to 30 meters per second in our test section. Then we have a burner here which will heat up this air up to like 440 Fahrenheit, so we can have this hot air simulating combustion gases. Then we have a settling chamber where we try to make this flow as uniform as possible coming into our test section. And this is where everything happens. So right here on the back side, we inject cool air, just like I showed you earlier, so you have the two streams merging. So you have hot air going in this direction, and tangentially you have cooler air. And then we have our test plate on the back, which is basically what we're trying to see how this plate will get heated up as the fluid passes over it. So we have several diagnostics. One is a micro thermocouple. You probably can't really see it, but it's a very small, basically electronic thermometer. It's smaller than 1 millimeter. So when you insert this probe anywhere into the test section, you can basically get a point measurement of temperature. And if you move it away from the wall to the outside, you will get basically temperature profiles. And then you can compare these later to theoretical correlations or to computer models. Something else we do here that you can't really see right now, we don't have it here, but it's a laser-based system to measure velocities. So just using lasers and some particles that you see into the flow and computer algorithms, you can basically obtain the velocities everywhere. So basically, because it's a mixing flow of two different velocities, the velocity in the flow will be different depending where you look at it, and you want to measure that to obtain a better understanding of what's going on. So we do that on that side. And then finally, since what you're really interested in looking at is exactly how well are you cooling this test plate, you would like to measure the plate's temperature. We use infrared thermography, which is a camera similar to like night vision. It's infrared, and it allows us to measure the temperature on the backside of the plate. So now we have everything we need, and it's measured simultaneously. So we have flow velocities, we have flow temperatures, and we have the plate temperatures. We're able to process this data and gain a better understanding of how the film cooling technique is working and how everything is acting at the same time to protect our test plate from the hot gases. So on another side, some other colleagues of mine have been doing computational simulations of the same phenomena. And basically what we do is we compare these results. We compare the simulations to the experiments and see if they agree, in which they do. They agree pretty well. And what this lets us do is validate the use of computer simulations for other conditions. So you need experimental data to validate the model, and then you can take it from there and just use your computational model over and over to simulate real problems. And this is the objective. Is NASA is actually sponsoring this for the J2X, which is the next generation rocket engine that will go back to the moon and to Mars. And these experiments are basically the basis for this computational model development effort. So overall, we have done a pretty good job here, and that's pretty much it. That's film cooling at the University of Maryland for you. Well, and just talk about my experience here. It's been a great 3 years working for Dr. Marshall, Fire Protection Engineering, Dr. Chris Cadu at Aerospace Engineering. They are great advisors, and I had lots of fun. There's a lot of hands-on work here, basically building this. I didn't build the whole thing, but I did get involved in building this test section, working with lasers, making measurements. It's fun. It's hard work, but in the end, it's fun. And when you see your results in the end, it's very satisfactory. So I'm very happy to do this.